I'm not very good at this, but maybe with a little practice, I could tell myself to relax it. Will be better next time I try. And even if I still can't do it, yeah, you know that I'm gonna stick to it. Yes, it's all about going through it, and I'm gonna tell you why. Whoopsie, whoopsies, I made a mistake and it's okay. It's okay. Whoopsies are what it takes to get better and better every day. Whoopsies, I made a mistake and it's okay. It's okay. Whoopsies, help me look, see, I'm better at this today. Woo! Whoopsie, 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 whoopsies.
I'm a little embarrassed when I look at my drawing compared to this. I'm just not getting anywhere with this. It makes me wanna hide. Aw, don't be embarrassed. Don't hide.
You should have seen mine the first time I tried. It took a lot of whoopsies to look this way.
No one's perfect on their first day. Whoopsie.
Whoopsies, I made a mistake and it's okay.
It's okay. Whoopsies are what it takes to get better and better every day. Whoopsie, 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 whoopsies.
Well, what about this? I want to jump rope, but nope, I just can't do it.
Well, not yet. Come on and practice with me. You'll see there's nothing to it.
Whoa! Whoopsie.
Whoopsies, I made a mistake and it's okay. It's okay. Whoopsies, help me look, see, I'm better at this today. Woo!
It was only a dream, the waves of evil crashing over us. It was only a weak and faithful scream beneath the battlements. I know it's hard to follow before it's too late. Wake up, my love, please don't give up on me. It's hard. Wake up. It was only a dream, the waves of evil crashing over us. It was only a weak and faithful scream beneath the battlements. But I know it's hard to follow before it's too dark. Wake up, my love, please don't give up on me.
What is up, you guys? My God, it's been so long since I've seen you guys. A whole 24 hours. We need more time apart, alright? This is getting a little too much for me. No, I'm just kidding. Let's go. Welcome to day 2. I'm glad to see all of you guys here. We know who's the real G's, alright? Everyone here, alright? The viewer count's way lower, just what I expected. Now we got rid of all the fakies. It's just the cool kids now, alright? Alright, you guys. Well, it's great to know that your heads didn't explode too much from yesterday's mathy shenanigans. And if it did, it's alright. Your head exploding, that's a normal thing. You just kind of got to get used to it when you're programming. It's what fuels a lot of programmers like me. I like it when I feel so angry, I want to break the computer in front of me into small pieces and yell at the world like, why? 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 But if you were at that state yesterday, then perfect. You are born to be a programmer, right? So, before we move forward, are there any questions that you wanted to ask from yesterday that you didn't get to ask, etc., etc.? And while you guys potentially ask questions, let me go and pull up some stuff here. So we did release a companion guide yesterday after popular... I don't even know what I was going to say. After lots of requests. So, effectively, we can't really give you guys access to the Learn site because it's not that simple and we're migrating everything already. So we're making companion guides. These will be launched pretty much almost every single day, if time permits for the admins. And basically, it's just a summary of everything we covered. It's going to follow the format of general overview, linking to the stream. After that, general topics we talked about. So we talked about rootkit. We had some quick mentions, and the main meat and potatoes was sets and relations. Underneath that, we'll have a quick overview, then some flashcards, which were made by a Discord member, Wolf. Thank you very much, Wolf, for making those. If you guys want to also help contribute to these, that would be awesome. Then after that are some challenges. So these are going to be questions, other challenges and quests that we have for you guys to accomplish. These are totally up to you if you want to do them. All the answers are going to be at the very, very end. Now, not all the questions are going to be easy and straightforward, and not all of them might be covered in what we talk about. Some of them are challenges. They're something that's a little bit extra or requires some creativity, or maybe something that's taught on the next day, aka today, to really figure out. And if you can figure out the challenge before the rest of the information is kind of revealed, then bam, you're golden. So that format's pretty much exactly the same for every major topic. The only difference is some of them may have supporting videos. So if you didn't understand something, or you think I was doing a bad job at explaining it, here's some extra videos for you to really consume those topics and see a different perspective on them. Sweet. Let's see if we had any questions come up. Nope, no questions. Yep, today is labeled, oh no, math. Because we're just going to be continuing forward with discrete mathematics here. I promise you it gets way, way easier with this stuff. We pretty much just had to get through the basics, the terminology, etc., etc. Now you'll see more and more how this kind of intertwines with programming, and we're going to do lots of programming examples here on the side. So let me open up, I thought I had VS Code open, here we go. So we can have this on the side here. So for those of you that want to follow along, we're not really going to be teaching the programming aspect just yet, but you are free to download this application called VS Code. It's basically the toolbox for a developer. Imagine you're a novelist writing a grand novel. You're going to sell millions and millions of copies of it. You wouldn't use just notepad, right, to write your novel, you would use Word. Effectively, that's what this is. It's like Microsoft Word, but for programmers. So throwing that into the chat. Awesome. So that's in the chat. You can go and download that. If you want to follow along, I'm going to be using this editor. We're going to be using Python. And again, we're going to go through all of this stuff more in depth at a later date. So this is more so for the people that really want to do something extra. If they thought the math wasn't challenging enough to try to follow along with, they can also try to follow along with this stuff. All right, so let's do a quick recap. Let's maybe go over the guide here. Where is it? One of these tabs. So we talked about rootkit and how we're the best thing since sliced bread. And that there's really no bad angle here for you. No one gets screwed over at the end of the day. We help you and you help us effectively when you get hired. Hopefully. There's no binding contract yet. Maybe I should make one, all right? Maybe we're screwing ourselves too hard right now. We get you hired and that's it. We're hoping you, maybe slide us a 20, under the table or something. But it's totally up to you. Let's see, quick mentions. We talked about some basic computer hardware, things that you normally mess with every day. You got your monitor for a phone. This would be the monitor, your screen. Your actual computer is the whole phone. Computers and phones are exactly the same thing. They're built exactly the same way. They have the exact same components. So just various items there. The big thing is memory. Memory is different than storage. Keep that in mind. If you don't really know the distinct differences just yet, just know they're different. All right, that's the main point. Let's see, the challenges. Know the difference between a computer and a monitor. Monitor is the pretty screen where you see all the nice pictures and graphics. Computer is the machine parts. Let's see here. Hardware and software. Everything you can touch, hardware. Everything you can't touch, software. A pixel. Pixel is little 3 light bulbs on your monitor, really close to each other. They form one pixel, which is usually in a box shape. Those are on your monitor. That kind of answered both of these. That's where you get RGB from, because all pixels are made from RGB. Red, green, blue, all right? There's always asterisks for all this, because there has been TVs released in the past with yellow pixels or yellow lights in the pixels to make 4 lights, but those are lame TVs anyways. They don't even exist because they sucked, all right? Not anymore, at least. Is memory for temporary or long-term storage? Memory is for temporary, all right? And then we got our math stuff. So we got all these symbols that we went over that are just aliases for normal human language, and they're just there to kind of make things a little more complicated. We gave you guys a challenge to go explore a little bit, and then we had these check on knowledges. So the first one should have been pretty easy for most people to eventually figure out. The other two were definitely a little more on the challenging side, and we'll go over this stuff a lot in the lessons that we have planned today. This one should have been, it's an upside down U. So a normal U that's not italicized is for union. Union, think of marriage, together, everything included. That means that it would be both of them, everything included. We're not performing a union because this is upside down. What else is upside down? The Satanist symbol, cross upside down. It's the opposite, all right? It's the opposite of union. It's everything that is just the intersection of those items, which I guess is kind of not really, whatever. It's the intersection of the items. So it's only the items that are similarly shared between them, but nothing else. All right. And if you needed the answers, they were all here on the last one. So if we look at 1, A and E, if we look at this, for A, there's a bunch of guys in here. And for B, there's a bunch of guys in here. And if we look, A is in here, A is in this one. B is not in the second one, C is not in the second one, D is not in the second one, E is in the second one, and the rest of these are not in the second one. So the only intersection they have is A and E. All right? Let's see here. What is the alpha channel in RGB? Yeah, it would be RGBA. There is no alpha per se in actual physical world. It's just straight RGB. The alpha is done through software simulation of things being layered on top of each other or being transparent. But in reality, I can't make a piece of paper more transparent. It's just whatever it is. Let's see what else. All right, sweet. So let us move on. Let's get some of that music playing in the background again. Where the heck did it go? Hopefully it's not too loud. Let me turn it down just a little bit. All right, sweet. So let's pull up what we'll be going over today. It's somewhere here. All right. So we are slowly banging through this list. We are just about halfway through sets and relations. We're going to try to get through the rest of this and maybe start diving into some of these other ones so we can just chunk through this list. So you'll see there's a common format that's happening here, and it's these curly braces with commas. This is just how you format a list, or in the math sense here is a set. So if I, in normal human land, want to make a grocery list, I'll probably click on bullet point or the bullet points and say like banana, apple, pie. All right, that's normally how we think of a list, or we make a list, is like this. In this world, we're going to use curly braces, which if you guys don't know where they are, if you're using a normal standard QWERTY keyboard, they're right beside the P. You have to hold shift to, it's on the brackets, you'll have to hold shift to get these guys to come up. And in there, we would instead write banana, and then a comma denoting that we want to have another item that's separate, apple, and pie. There we go. If this is how most of the math ways will have it laid out, but it's kind of heathenistic to do it this way, at least in programming realm. We are more akin to nice layouts, so we'll usually format things more like this, which will look familiar for anyone that has some programming experience, because this is normal syntax for a lot of stuff. But I mean, this also looks a lot clearer, but it's not dense informationally wise, so you know, it's better to put it this way for a lot of reasons, just because you can fit a lot more on the same page. But just so you guys know, let's go ahead and take a look here. So let's run through some examples using this new confound math contraptions that we have. We have our union. So they got some examples here for us. Let's go ahead and grab these and paste them right here. And let's together solve some of these problems. And by together, I mean, let's see if any of you guys can solve them first before I reveal the answer. Don't look right here, because it has the answer. All right, shh, you didn't see them. Bro, thanks for the Patreon membership. That's epic. Make sure you claim your Discord membership so you get access to the supporter chat and all the additional benefits. And I can't remember what perks come with the Byte tier, but if it came with stickers, those will be sent out to you soon. All right. So let's see here. We're wanting to perform a union for the first one. So in the chat, what will this equal? What is the new set that this will be? Any guesses? Don't be nervous. All right, it's all right. I believe in you. Yeah, no duplications. Let's see. We got Astro said A, B, C, D, and E. Epic. So let's see here. A, B, C, D, and E. Perfect. That is correct. And let's just manually look it over. This is a U. U is union. Union is together, which means it should be a set of everything together. So let's look at A. A is A, B, and C. We have A, B, and C. Perfect. B is B, D, and E. And we have a B, D, and E. Perfect. Sets are, again, I don't know if I mentioned it before, they are just one of every unique item. Perfect. Flawless. Now let's do the next guy. Anyone want to put in something for the next one? I'm going to go ahead and copy some of these over here so we can just continue down the line. All right, any guesses on the next one? Come on, I believe in you guys. You'll put in the answer for the other one. So this is intersection. So it's going to be everything that intersects. All right, I got a B and oh, someone answered another one. All right, we're going to go with B for this one since that's what I see. So let's look it over. So this is intersects, so it's everything that intersects between the two. So let's check this. A is not in the second one. B is in the second one. And C is not in the second one. So B is the correct answer. B is what intersects between both of them. And if we look here, yep, there's a B there too. So this is the absolute complement. Guess what? I barely remember what the absolute complement's for. So what do we do as professional programmers when we barely remember something? The key thing is you remembered the name, absolute complement. If you don't remember what it is, guess what? You ain't in school anymore. You're a grown-ass adult. Open up a new tab and type in absolute complement into Google and get your answer. Let's go look at some pictures. Look at that. Absolute complement. All right. It's everything that's not in the first set, right? That's what it looks like. I don't know why they have the slash there. Is this not absolute complement? Am I messing it up? Oh no, I need to go back to school. All right, let's double check ourselves here. Yes, it is absolute complement. I don't know why that one graphic. This is why you shouldn't trust everything on the internet, kids, because that is I think that's the proof for it. Whatever, we're moving on. Everything not in the first set. So if we look in here and we look at A, well, A, B, and C are in here. So we can't have A, so we're not going to put A in here. We can't have B, and B is in the second set, so we're not going to put in there. And C, we're not putting in there, and C isn't in this set. So this one's going to be a what? I see someone put D, E, and F. Perfect. because this also includes everything in the universal set. So if we look, F is in the universal set, F is not in A, so we're good. I should have been comparing A against the universal set in the first place, so that's kind of, that might throw some people off. But if we look again at the picture, it's everything including like the box, which is, the box is a universal set, aka everything that's possible. So it's everything except what's in A. Alright, let's move on. I think someone answered this one before. Let me see. Someone said A and C. So let's check this one out. This is the relative complement, I believe. There we go. There's our picture. So it's everything in A except the things that intersect with B. So everything from A. So we would want to originally have, let's say, A, B, C in here. Does A belong into B? No. Is B inside of this B set? Yep. So let's get rid of that. And C. Is C in here? Nope. So this is the correct answer. So you are 100% correct, Milo or Milo. That is the correct answer. Epic. So let's get on to this last guy. This last guy we got right here, the symmetric difference, which is everything except what is similar between them. Does anyone have an answer for this guy? Let me check the Twitch chat here. Nope. Any guesses? I got a thanks for following us, Mr. Unrighteous. Man, you need to go to church or something. Alright, C, D, E. There we go. So, this is our guess right now. So it's everything that's not the same between the two sets. So let's see. A is not in B, so we can put it in there. B is also in the other one, so we can't put it in here. C is not in the other one, so we'll put it in here. D is not in the other one, so we'll put it in here. And E is not in the other one, so we'll put it in here. Epic. Congratulations, you guys. The math that you've just performed is usually in college requires you to take calculus first. So you should feel proud of yourself. This is supposedly some high-end complicated math for people that are only taking calculus, okay? Because your minds apparently aren't big enough to comprehend it. But if you ask me, I think you guys got this stuff in the bag, all right? So let's go ahead and continue forth. So we just solved all of these example problems. Now, if you think back to school, you might have heard this term PEMDAS. I don't know if that rings some bells, but it's basically an acronym for how you're supposed to solve any given math problem and in what order. So P stands for parentheses. So anything in parentheses you would solve first. Then E stands for exponents. Correct. You're right. Then next is multiplication, then division, then addition, and subtraction is last. Pretty much this holds true even for discrete structures, except you don't have some of these symbols. So instead, anything in parentheses you do first, just like in PEMDAS. Then absolute complements are done second. And then finally you do unions, intersections, relative complements, and symmetric differences. So when you're given compound questions like these, it's important for you to solve them, in the correct order. So in the handout we gave, you'll notice that we tried to break your brain a little bit with these last two problems. These last two problems to have solved correctly, you would have had to make the educated guess of, hey, this kind of looks like an exponent, so maybe I should solve that one first and then do the rest of the problem. And then same thing with this. Looks like an exponent, so you would solve this one first, then and also this one first, and then you would perform this operation. So the easy way to think of it is parentheses first, exponents second, everything last. Just kind of like how PEMDAS starts, you know, parentheses first, exponents seconds, and then everything else. All right, so this kind of breaks down how you would solve one of these guys. Let me go ahead and put him right here, and let's just take a look at it ourselves. So we know this is an absolute complement, which is everything in the universal set except for what's inside this original guy. So let's copy this problem down below, and we won't do this stuff first. You know, first part, let's do this. So we know it's going to produce a new set, and in this world we use curly braces to dictate a set. So in our set we have everything in the universal set. So everything right here, let's go and copy this guy down, except what belongs to B. Alright, so we copy the universal set, so we got all the items. Let's see, A does not belong inside of set B. B is in set B, so let's go ahead and delete that guy. Here's D. D's right here, so let's go and delete that one. And E. E's right here, so let's go and delete that one. That is our answer. And so that's what we have right now for our current breakdown of how we're going to do this. Now, to furthermore simplify this, let's just get rid of this weird A symbol, which is called a variable, and a variable is a placeholder for some type of data. So we have a great YouTube video on that where I hammer in that point very, very hard. It's just a placeholder for data. So what does that mean? Well, let's get rid of this placeholder and put the raw data right here that it's representing. The raw data it's representing is a set. What is that set? It's the set of these values. Epic. So that's all that guy is. So now we just need to find the things that match between them. So let's go ahead and look. I see A's in both of them. So let's go and put an A here. And B is not in both, but C is. So this would be the answer. A, comma C, our new set. So just step by step, breaking it down. It's nothing super complicated. It's almost like, you know, just a simple childlike behavior of, does this color match this color? Except in this case, it would be, does this letter match this letter? Depending on the rules that you're going for. So this would be intersecting. So I know all of you guys are 100% capable of doing this stuff. 100%. Hopefully for most of you guys it's clicked. If it hasn't clicked completely, just let me know and we can go over some more examples. So if we look here, we have the same result. So thank God I was correct. So we also got this pretty picture right here that kind of shows off this problem in a more visual sense. We won't really break into or dissect this too much, but you can visually draw out all of this stuff if you would like to kind of see it more in a different sense. Are there any questions on this before we move on? All right. I don't see any questions right now. So time to throw in some familiar symbols that you've seen before and should make you feel a little more comfortable and then slap you in the face and then make you feel uncomfortable. All right. So terminology of relations. This might be difficult for some of you guys in here who have difficulty with relationships, but don't worry. This is Dating 101. We'll get you through it and you'll be back out there slaying real soon. All right. The order of elements in a set do not matter. They don't matter. You can order them however you want. If you like A, B, and C, like being in alphabetical order, cool. If you're weird and you like everything being in reverse alphabetical order, cool. Or maybe you're just a spawn of the devil himself and just like jumbling everything together. Hey, you do you, I guess. We're in 2022, man. Alright, oh god, we're in 2023 now. Never mind. For example, the set routers and switches. Routers and switches are pieces of hardware that you'll be utilizing in the computer world. You can have a set of router and switches, but if you switch those around so it's switches and routers, it doesn't matter. It's still the same items, regardless of the order. Just because I have a pen in this hand and a book in this hand, and I switch them around, doesn't mean I have a new pen and a new book. They're the exact same two items. They're just in a different order. It doesn't matter at the end of the day. So if you would like to have an identifiable order in a set, use parentheses to represent them as an ordered pair. For example, they got parentheses here, routers and switches, where routers is the first element and switches is the second element in the pair. So let's pause for a second. Like I said before, we've been using curly braces to denote that we have a set or a list of items, and the order does not matter for those ones. But if you, for some reason, really need to make sure the order is important, I don't know, maybe you're making a list of instructions for someone for something crucial. I don't know, like, is changing brakes on a car important set of instructions? I don't know. It might be important, I guess, for you to have everything in the right order to make sure the brakes work. I don't know. It's up to you and how much you like that individual. But that is a case where you would want the order to stay intact. So let's see here. Let's move on. The Cartesian product of two sets, A and B, is the set of all ordered pairs where A is an element of A and B is an element of B, denoted as this. Cartesian product. Fancy term for multiplication, alright? I know all of you guys have performed multiplication at some point in your life and you still remember it to an extent. I hope you can at least perform it on a calculator. It's just multiplication. It's multiplication with multiple items at the same time. In this case, sets. We'll go through and break down how you would perform it. But they say it's read A cross B. If you say A times B, I ain't gonna judge you, right? I'm gonna probably use that term moving forward. But this is the proper way of saying it. So if we have a set A, which is 1, 2, and 3, and we have a set B, which is A, B, and C, then A times B equals this big guy. So, holy crap, what just happened? There's a lot of crap going on right now. Let's break it down a little bit. So, let's copy this problem, go to a new page here, and paste it. Now, like I said, this is multiplication. Normal, basic multiplication math. Technically, this is entering into the realm of like statistics. But oh, don't get scared away from this. It's way easier than you think it is. Let's start in the normal multiplication realm where we're all very familiar. We have 3 items in this set. 3. Let me actually put it up here. We have A equals 3 because there's 3 in the sense that there's 3 items. I guess I should write 3 items in the set. And B is equal to also 3 items in the set. Both of them have 3 items inside their set. If we do normal math, A times B, which these are variables. So variables are what? They are placeholders for data. What that data is, who cares? It's just some type of data. Maybe it's a picture, maybe it's a number, all right? So this would look like 3 times 3. Oh gosh, that is not a 3. What's 3 times 3? No, it's not 10. Come on. What are you guys, comedians? All right. It's 9, all right? So we know we're going to get the result 9. And if we count out how many are here right now, we got 1, 2, 3, 4, 5, 6, 7, 8, 9. So cheat number 1. We know we're supposed to get 9 results. All right, so we can kind of work off there and maybe cheat our way to the answer if we don't really know what we're doing. Myself. So let's on. I see some comments coming. If possible, could you zoom in on the text on the website a little bit? Yeah, 100%. Let me go ahead and make this bigger and zoom in more. Does that help out you guys? Or I could also do. No, I'll just zoom in. There we go. Wait, it's not 3? Get out of here. So 3 times 3 is 9. So we know if we see a set problem with multiplication, basically to help us out a little bit, we can just count up how many items there are and just do a normal multiplication question. So 9. We know we're supposed to get 9 items as an answer. So how do we get these guys? Well, let's go through it a little bit, shall we? So, let me look here real quick. I'm just looking for specific terms. So, we have A, which is a 1, a 2, and a 3. Now, when you see curly braces, order doesn't matter. So, what we can do, we're making a new set. So A times B, or A cross B, is producing a new set, like everything, excuse me, everything else. And a set is just a piece of data. A number is a piece of data. A picture is a piece of data. An NFT is a picture of data, or a piece of data. And I know you guys love your NFTs out there, right? All right, so all it is data. So you can put a set inside of a set because it's just data at the end of the day. Who cares? It's just data. And I could put a set inside of a set, inside of a set, inside of a set, inside of a set, and go on forever like it's the Matrix, all right? Data can go inside of data. So inside of here, we know we need to have 9 results. So to do a little cheating, we can just copy and paste 3, 4, 5, 6, 7. I think I just messed something up. 8, 9. All right. So we have the baseline here. At least we're making steps forward. We don't have the answer yet, but we're making steps forward. All right, sweet. So how do we start filling this out? So if you think back to math, I don't know, maybe this was like pre-algebra. You guys should have all completed pre-algebra, hopefully. If not, it's all right. This is like the only time where pre-algebra might have helped you in the real world, all right? So it kind of works similar to if you were to do multiplication against polynomials, if you remember that. If you don't, then forget I just said that, all right? Basically what we're going to do is we're going to take the first item in list A, 1, and we're going to do it 3 times. And then we're going to take the second item and do it 3 times. And then we're going to take the third item and we're going to do it 3 times. And then we're going to put commas at the end of all of them because they need to be combined with the second item that we're multiplying against, A, B, and C. So basically you're making every possible combination between every item in A and every item in B. So A, comma, or 1 comma A, 1 comma B, 1 comma C. And then for 2, 2 comma A, 2 comma B, 2 comma C. And then 3 comma A, 3 comma B, and 3 comma C. This is every possible combination of these guys when order doesn't matter. So of course A, comma 1 would be different if ordered matters, but since we have curly braces, order don't matter at all. So it's every possible combination. So we can start with baby steps to figure out exactly how many combinations we're gonna need as like kind of a checking ourselves. And then we can sit here and then write out every combination. All right, don't worry about the math part, XYZ. It's a simple process of let's try to figure out every combination that exists. All right, that's all it is. Let's see, you're throwing out terminology and all I remember is muscle memory. Yeah, if you guys are confused with any of the terminology, please let me know. I can refresh. The big thing that's important is this multiplication across, and that you can do multiplication at first to do a self-check to see how many you're supposed to have. So we're supposed to have 9, and then you can hand jam and figure out what every combination that is possible out there. I find it's easiest when you do, you see there's 3 items in here, so you'll just put the first item 3 times, second item 3 times, etc., etc. And then the next one, you'll just do the first item, second item, third item. First item, second item, third item. And you'll keep going like that, just that pattern, and then you'll have it solved. Any questions on that before we move forward? So the above example shows element 1 from set A has a relationship between the element A from set B. So that's what a comma means, is these guys are related in some capacity. What capacity? I don't know. 1 and A. Alphabetical order, I guess, is the first letter of the alphabet. That's a pretty reasonable relationship, but now these are thrown off right here. Regardless, that's what it's meant for showing off. Next, if there are no questions on that, is the power set. That is 2 by the power of another set. So this is different than the absolute complement, which is the set to the power of usually C, because C stands for complement. This is 2 to the power of whatever set you want. And that's how you make a power set, all right? And a power set will always include the null value or an empty set. Why? It just does, all right? Stop asking questions, all right? I'm just kidding. Keep asking questions, but that's just how it is. Just include it and call it good. Get your 10 points for the day, all right? So if A is equal to Claire, Matt, and Josh, then the power set of A would be this. So let's kind of break this down a little bit. Because again, at the end of the day, variables are just placeholder for data. Your variable doesn't have to be A, B, C, X, Y. It could be anything, right? Just single letter variables are usually a little easier to write out because we're lazy at the end of the day, all right? So when we're doing the power set of A, our new set is going to have pretty much the same thing, every possible combination of itself. If that kind of makes sense. It'll make sense here in a second. So first, you always start with a null. So a null is an empty set. Remember that this weird term or symbol is the exact same as this guy. They're just the same picture for the same meaning. So we'll start with something empty. Then there is Claire. So we'll put Claire by herself. And then there's Matt. So we'll put Matt by himself. And then there is Josh. So we'll put Josh by himself. And then we'll put Claire and Matt together into one set. And then we'll put Matt and Josh together into one set. And then we'll do, we can't forget Josh and Claire into one set. Claire and Josh. So that's every combo of this, of like these two matching. And then there's only one left, which is the original, all three of them. Oh God, what have I done? Oh no. There we go. So that would be the answer. It's basically every combo of like every arrangement of those three items you can have. And I believe, how many we got in here? 1, 2, 3, 4, 5, 6, 7, 8. So this should be the same if we bring up our trusty calculator here and we say 2 and then 2 to the third. That is not the right one. God. 2, I thought it was, where is Wolfram Alpha? Wolfram Alpha. There we go. If you haven't used Wolfram Alpha, you should use it. It's the best calculator in the world. Alright, so 2 to the power of 3. There we go. That's what I wanted. So just like the other one, can I click on it? So just like the other thing I did, you can do the basic math, replace the little A here with just how many items there are. So there's 3 items here. Just like how there were 3 items for each of these. Except here we multiplied them because the cross is usually for multiplication. Here we have 2 to the power of something. So if you want to confirm how many items you're supposed to have, if you do 2 to the power of how many items there are, so in this case there are 3 items here, you'll get 8 as your answer. So we know we're supposed to have 8 items. And if we look here, including the null one, we have 1, 2, 3, 4, 5, 6, 7, 8. We have all 8 items, so we have solved this one correctly. So again, this one, you just include the null. Just include the null whenever you see this one. And it's every combination of all 3 of those items when order doesn't matter. So Claire by itself is one combo. Matt by itself is one combo. Josh by itself is one combo. Then Claire and Matt is one combo. Then Matt and Josh is one combo. And Claire and Josh is one combo. And then all 3 of them is one combo. That makes sense? Any questions in regards to that? It's pretty much just matching games. A lot of matching games. I don't see... Oh, here we go. So with all 2 to the power of A, you include a null first. Yeah, the null... I mean, so since we're using curly braces, order doesn't matter. So null can be anywhere. You just need to make sure you include null in there somewhere. But null is something you always have to include when it's 2 to the power of something. When it is a power set. This is the only time out of all the things that I've shown where you will by default include a null in your answer. Yep, anywhere else a null is included. Nope, nowhere else, just power set. It's the only one that will ever have a null in it. So let's go on to the last guy. This one is I promise you, this one won't break your head. This one is actually really, really easy. All right? There are these symbols called the pipe. You might know these pipes from Mario. Very famous, that man made these pipes. All right? The pipes are usually right above your enter key. It's just straight up and down. You have to hold shift and then press the key for it, and then you'll get a pipe. So effectively, remember when I broke this out and got the answer 9, or I broke this out, I didn't really write it down, but got the answer 8? The pipe is basically saying, revert back to normal math, all right? It's effectively saying, let's grab this whole thing. And let's get rid of all the words so we just have the horrific math by itself. So if I say that, this is means absolute value. So basically count up how many items are in the set, and then that's your answer. So there are 3 items in the set, so the answer is 3. If I have another one that is going to be this times B, the answer is 9, because 3 times 3 is going to be 9. If I have one that is going to be the power set, but power set pipe, why is it, but why? What the hell? Alright, let's try that again. What is going on? Alright, we're gonna do a pipe space. Okay, well, there you go. Imagine those are right beside each other, but this would be 8. So whenever these guys show up, it's the absolute value, aka just count everything up and tell me how many exist in that set. So it's pretty simple. So right here it's just showing you the same thing. A times B is going to be 9 in this example, and then a to the power, or to the power of a is going to be just the basic math, which is going to be an 8. Aren't there 9 in a power set? No, there is only 8 in a power set. Or the null is counted. So with null it would be 1, 2, 3, 4, 5, 6, 7, and 8 combinations. That makes sense? Yeah, you're good. No, keep asking questions. These are good. Yeah, I don't want you guys to be like confused at all. Oh boy, we get more pictures now. So I'm not gonna say anything now, but I think the curly braces on this doc were supposed to be parentheses, but we will move forward. All right, it's not something that will fail you too hard. More so, again, it's the understanding of these general concepts. Again, if you missed it from last time, when you do our certification exam, it's in 2 steps. One is the writing portion, which isn't really writing anything. It's just multiple choice questions for most of it. And it's 100% open book. You can Google stuff. You can use your notes. You can do whatever the hell you want. It's completely all free game. The only thing is you kind of do need to know the items, because there is a timer on it. And if you don't solve it in the right amount of time, you're going to be donezo. If you finish that, then the second part is the programming, or the practical exam, where you actually have to program out something that we give you. So yes, Osmium, that is correct for those 2. So he asked, if those would be the same. They would be the same, because at the end of the day they both evaluate to 8. Alrighty, so let's move on to Pictureland. So a relation is a set of ordered pairs that can be illustrated by a directed graph. Directed meaning there are arrows there are lines with arrows pointing somewhere. Graph meaning it's a drawing of arrows pointing places. A relation is defined by R italicized. Relations can have reflexive, symmetric, or transitive properties. Each is explained below with the set 1, 2, and 3, the set with the variable of s. So figure 7 below has s times s. So 1, 2, 3 times 1, 2, 3. So this is a way for you to, if solving it the way I went about it last time was not clear enough for you, this is an alternative you can do to solving it. So if we bring up our fancy paint, now I get to bless you guys with my beautiful artistry skills. All right, don't shield your eyes. You're gonna want to watch this. All right, so if we have some type of set, we're not going to call it S because S is too generic. Let's call it, I don't know, apple. Our set of apple is equal to, oh, look how beautiful my drawing skills are. Y'all are just so spoiled. All right, 1, 2, and 3. That looks like a 3 eating a 3. All right. We can draw this out if we get the question of apple times apple. If we like pictures, and I like pictures, pictures make everything easier, we can draw this stuff out. All we have to do is first put everything out on here. So let's put a 1 here somewhere, a 2 here somewhere, and a 3 here somewhere. When we're timesing things, all things will be pointing to themselves. So we can take item number 1 and draw an arrow to itself. We can take item number 2 and draw an arrow to itself, and draw an arrow to itself on the last item. All right, sweet. So we've solved pretty much half the problem so far. Take just a quick peek here. And we got to do some pointy elsewhere. So it looks like they're starting from 1. And so the first value that you have here, the first value should point everywhere else. And then we need to bridge the gap here. And it looks like the next lowest value. So we start at 1, will point everywhere. Then 2 will point everywhere it can, which it can only point there. And then that's the picture way of solving this. So then we can go over to our book here. Let me look through this again. 1, 2, 1, 3. There we go. Okay, so this is going to reflexive, symmetric, transitive property. Kind of, okay, we're just gonna keep solving it. So this would be written, oh gosh, this would be written out as 1 is pointing to itself. So we have a base set, and these are going to have parentheses because they're ordered, so order matters here. So 1 points to itself, so it'd be 1, 1. That's the relationship here that we're showing off, is 1 has a line that is pointing to itself. So 1 is 1. Then 1 is pointing to 2. So 1 to 2. And also 1 is pointing to 3. So we're going to have all 3 of those. So we just wrote mathematically this line, and this line. So we're done with those guys. So then we go up to the next item in the list. So we started with 1. So now let's go to 2. So 2 is pointing to itself. So let's go ahead and do a comma, and a 2, comma 2. Whoops. So we got rid of this one. And then 2 is pointing to 3. So let's do 2, comma 3. And we'll cross that one out. And then the last one is 3, comma 3. And there we go. We just did this whole little graph here. So let's look back on this guy. And let's go to the next item, because I think this is just showing just a generic picture of how you would go about all of this stuff. So let's talk about reflexive. So whenever you hear the word reflexive, it's everything that every element is pointing to itself. So everything is going to have the little circle around. So if we undo. If we want to say what's the reflexive set of 1, 2, and 3, it's just this. 1, 1, 2, 2, and 3, 3. You can draw it out, or you can write it out like this. Let's see. This would be irreflexive if A or A for all in S is not true. So there's an opposite for reflexive, which is irreflexive, which means that if the connection A, RA, so the arrow starting from A, or element 1 in this case, points to element 1 for all in S is not true, it would be reflexive. I don't think we have an example of that because I don't know when that would ever be true. But reflexive is everything pointing to itself. Actually, it would be, okay, I see, sorry. If I have a list and I tell you set banana is equal to this, and I ask you, is this set reflexive? The answer would be true. It is reflexive because everything in the set is pointing to itself. And then if I asked you, is this reflexive? No, this is, what was the opposite of reflexive? Irreflexive. That would be your answer, because not everything is pointing to itself. Because 2 is not pointing to 2, it's pointing to 1. So this is just terms for things that point to each other. So reflexive means that every item in the list points to itself. Irreflexive means that at least one of the items in the list are not pointing to itself. Then there's symmetric. So symmetric implies that A points to B and then B points to A. Or in this case with this picture, 1 is pointing to 2 and 2 is pointing to 1. It's like that meme. God, what's that meme called? Oh no, where they're like you and the other guy's pointing. It's the Spider-Man meme on. Spider-Man meme pointing. There we go. What a beautiful meme. Oh gosh, not that one. What is this? Why is this a promotional thing? Alright, this meme right here. I want you to think of this meme when you hear symmetric, alright? Because the items are pointing to each other, right? So when they're pointing to each other, they are symmetric. So if you have a list, if I give you a generic list that says, I don't know, red and green, and then green and red, and I ask you what type of list this is or a set this is, you'll tell me that it's Spider-Man. I mean, symmetric. Very good. Can you go over reflexive and irreflexive one more time? Yes, I can. So, reflexive, think of reflexive as God, what's that one guy's name? Yeah, I know, very descriptive. Susanna, what's that one guy's name? Andrew Tate. There we go. You're Andrew Tate. Andrew Tate loves what? Okay, not just money, but he loves himself. He is all about himself. He thinks he's the coolest shit, and I think I'm the coolest shit, alright? It's all about that self-love, alright? Reflexive is pretty much the same way. Like, you're pointing at yourself. You're saying, hey, look, I'm cool, alright? That's reflexive. So every item in the list needs to be related to itself. So if each element is related to itself, you can also think of this as inbreeding, alright? Everything is related to itself. Kind of a interesting take on it, but I think the like I'm cool take is probably better to use, alright? But everything is pointing to itself. That is reflexive. So if I give you a list of Andrew Tate and Andrew Tate, whoops, there we go. And then I give you a list of Elijah and Elijah. This is 100% reflexive list because everything in here is pointing to itself. If I say Elijah and Shu, this is not a reflexive list because not everything is pointing to itself, alright? So everything has to be pointing to itself, and that's where the pretty picture comes in of it needs to be pointing to itself. Every item needs to be pointing to itself to be reflexive. So irreflexive, so the directed graph below shows reflexivity with an arrow looping around from and back onto itself. This would be irreflexive if A, RA, for all in S is not true. So this is saying that if this would be if for all is not true. I believe this is for literally any single item. So this would be an irreflexive list because this breaks the pattern. One of the last guys I would think you'd... Look, I just needed some help, alright? So if anything breaks the pattern, it's going to be irreflexive. Now, these, you can have a list that is multiple of these items, alright? They don't have to just be one or the other. For example, symmetric, like I said, Spider-Man meme. They're both pointing at each other, alright? They are both pointing at each other when you draw it out and in the set. And there's asymmetric, when they don't point to each other. Just one person is pointing. So if I have something like, let's get rid of this. And let's say taco and food, I guess. Taco is pointing to food. So can I clear this out? Don't save. We got taco. If we draw this out, taco is pointing to food. I ask you to describe this list. It can have, you can use more than one word to describe something. All right? This is not reflexive, so it's irreflexive. What else is it? Well, it's not symmetric, so it's asymmetric. So this is an irreflexive, asymmetric list that we have right now. Does that make sense? Zoom out on that example. Which example? Or is this what you want? Of the irreflexive. Zoom out. Oh, zoom out on that example. Like, you want me to zoom out more? I'm kind of confused. Are there any other questions right now on these two guys? There's only one more left, I believe. Yeah, there's only one more left. All this is it's just words to, you'll find, I mean, depending on your age, you might have already like kind of self-discovered this. I was talking about the Andrew Tate. Oh, so this one, well, it's already deleted now, but what you'll find, depending on your age, as you grow older and older, is it makes life easy if you can describe things in the world, actions, as some type of word. So some of this stuff, you might be sitting there like, that makes sense. Or I might have done that before unconsciously, or just something else. All this is descriptive words to describe that type of action you're taking. I mean, it's used in, think of it like if you're trying to build a company, marketing, the iPhone, Apple, they constantly make up new words to describe something that you can do or you could previously do. For example, selfie. Selfie, the word selfie was invented like a decade, 2 decades ago. It's a very relatively new word. Did no one ever take a picture of themselves before that word existed? No, people did that all the time. There are plenty of selfies that were taken before the word selfie existed. But the word was invented so people can easily correlate, oh, I don't have to say the whole long sentence of taking a picture of myself. I can just say, or with myself, of myself, all right? I can just say the word selfie. It just makes things way easier, and you can associate that term with that like action. That's all these terms that we're learning right now is just a term that is associated with this action that is being taken place. So the action of you pointing on yourself, reflexive. The action of you not pointing on yourself, irreflexive. The action of you pointing at something and it pointing back at you, symmetric. Asymmetric, it's just one way pointing. It's just describing things that you can do. Does that make sense? So let's go to the very last one, and that's going to be transitive. So relations are transitive if A are B and B are C implies that A are C. So let's clear this guy out. So again, when it ever comes to math or programming in general, it's best to kind of, especially if it's something that's kind of crazy like this verbiage right here, it's best to really say it out loud. Maybe grab your pen and your paper and draw out what's going on. So lowercase letters stand for what? Lowercase letters in this context stand for elements. So elements in a list. So if we're drawing our picture, we have A. And at the beginning of this, it said that R, capital R, italicized is going to be the relation, aka the arrow. So this is saying that something is transitive if A points to B, so A points to B, and B points to R. So B points to C, not R, my bad. So B points to C. Imply A points to C. So what is this saying? Imply is the big important word here. So let me erase this guy. Is this really the biggest erase? Why is it so small? Doesn't make any sense. So what's going on here? Look, you guys are all very smart people, and you do this all the time. It's called an assumption, right? If I tell you that it's going to rain today or it's cloudy outside, you can assume that the color of the sky is what color? Purple, correct. All right? It's the same thing with this. You can assume something is true based off of how other things are set up, all right? You can assume that the sky is gray right now because it's going to rain today. You can assume that because all of the leaves are off the trees, that it is fall. This is, whether it seems like it or not, this does correlate pretty directly to how you take actions in the real world. It's just abstracted a layer up. So transitive is an assumption, because if A points to B and B points to C, what does that mean? Let's say this is a road that you want to take. You want to take road from city A to city C. Is that possible? Yes, it is possible. You just go from A to B to C. So since that is possible, you can imply that A goes to C. So A is related to C because you can go to C from A. That's what transitive is saying, is that you can imply something. So if one element is related to a second, and that second element is related to a third, then the first element is related to the third. AKA, you're implying, you're making that assumption of, okay, I know in my head if I want to, so I'm in Maryland, and DC is right below me, and I want to go to Florida to go to Disney World, all right? Disney World is below DC. So I know that I can go drive from my house to DC and then drive to Disney World. So you can imply that I have a direct route to drive all the way to Disney World, because I mean, even though I'm driving through DC, that's not the point. I'm driving to Disney World directly. Does that make sense? And that's what transitive is. Any questions on that? So how that would look on a list, let's say Bob, Joe, and Sam. Bob and Sam. So this is where the ordered pairs come into play, because when you're drawing this stuff out, ordered pairs are important, so you know where the arrows point. So let's say you're trying to build a social network, all right, and map out all these relationships that people have. So Bob, if I ask you, well, let's take a step back. If I ask you about this list and what are some properties of this list, you saying this list is transitive, it would be 100% correct. The breakdown of it to a more real world aspect is you're Bob and you have a friend named Joe. And that friend Joe has a friend named Sam. So if you wanted, you could communicate with Sam at any time by utilizing your friend Joe. So that's basically, that's like the real world concept of all of this. And you'll see more and more in the examples that we're about to do next, kind of how this all starts mingling together. Any questions on that before we move on? If there are no questions, should we do the check on knowledge together? Or should we just go to the next book? We're going to do a break first, but it's up to you guys whether we want to do the next book or do the check on knowledge. So I'm gonna go ahead and put us on break. We'll be back in like 3-ish minutes. If you have questions, go ahead and ask them. And then also put in there whether you guys want to do the check on knowledge together here, or if you guys just want to go on to the next book. All right? All right. I'll see you guys in a couple of minutes. All right. We are back. So, let's see here about the questions. I see someone's voting for check on knowledge. I took a little bit of notes on my iPad if anyone wants. Yeah, if you guys have notes, anything like that, feel free to share them on the Discord. We can add them to the companion guides that we send out, and we'll definitely make sure, you know, you get credited like we credited Wolf on his stuff. Let's see. I'd be down for pooling notes together. You guys totally should 100% pool those notes. I've never heard of it. Note-taking app on steroids. It's free. Epic. I like it. I love it. Yeah, so again, make sure you guys tell friends, family, everyone you know, post it, share it, but don't just do it. All right, do it smartly. All right, go over to the Rootkit website and then go to our blog. There's also a link on the announcements, and then click on Week 1 giveaway. When you click on the Week 1 giveaway, you can enter and get a bunch of points to enter the giveaway that we're doing at the end of the week. And we're giving away a bunch of merch. All right? And if you do... Where is it? Let me zoom in on it so you guys can see it a little better. Refer a friend. It's unlimited. Give people this link. If they sign up for the giveaway, you'll get 5 points. And it's unlimited usage, so you'll get unlimited points. So share about it on Facebook, Twitter, LinkedIn, email, or just copy this address and tell your friends and family. Get yourself some more points. Remember, again, the points, you only get the 5 points if they also sign up for the giveaway. But there's a bunch of points you can get here automatically for subscribing to the YouTube channel. And this watch a video daily is supposed to be the stream. I definitely haven't been keeping up on that, but get yourself all the free points. Also, remember, this is a charity stream. That is not the link for it. I think I can click on this. So we are raising money. So make sure you donate on here. Oh gosh. So we are raising money. Be quiet, fool. All right. So you can donate on here, and when you do donate, you can get stuff like merch, like the 100-day Rootkit stickers. I don't know why there's 2 of them there. That's a little weird, but there's the collab t-shirt, which is right here, super epic. I totally just didn't change my shirt just a second ago. You can also make me dance. It's super hard to see. I don't know why their site is like this, but there are goal points that we can hit, and after hitting some of them, I'll do things like shave my head or shave my beard. Don't raise it to this bar, please. I don't want to shave my beard. And the last one, we're not even talking about the last one because I hope we don't get there, all right? All right. So, yes, raising money, tell your friends, super awesome. I mean, if you were to go to college, you'd be shelling out $100K for this stuff right now. All right? We're giving it to you for free. No strings attached. Besides, get certified through us so we can get you a job, all right? So, let's see. Check on knowledge. Let's check out the check on knowledge, and hopefully I don't make a fool of myself. So, let's go ahead and attempt the quiz now. Which one is a union? By the way, pro tip, some of these questions might be the exact same ones that are on the exam. So pay attention. I didn't tell you though, right? I didn't tell you that. So what's the answer? Which one is a union? I'll zoom in a little bit so you guys can see a little better. B. All right, let's do B. Let's check it. That is correct. 100% correct. Human.exe scored us our first point. So let's go to the next one. Which one, or select one, is A subset of B? Not a proper one, just a subset of B. True or false? Yes, I should. Any answers? I don't know how delayed this stream is, but hopefully it isn't too delayed. True. Let's see. Check. False. To be a subset, A has to have at least... Oh my god! We got a donation, y'all, for $100. Thank you very much, Matthew Yes, Matthew. Thank you, Matthew. It says, don't have much hope, but I hope this helps. Wait, sorry. I need to read, y'all. I don't have much, but I hope this helps. I'm in college currently, and I can say this learning style is way better. Yeah, man. I love it that you're enjoying this, even though I'm kind of fumbling through some of these items, alright? But hopefully the relationships we're making with some of this stuff to the real world concepts really helps out. So let's go over this one. You got it wrong. Who cares? I get stuff wrong all the time. I've gotten stuff wrong even through the 2 days we've been chatting, right? So let's talk about it a little bit. This is how we learn, by getting things wrong. So subset, A is a subset of B, which means A has to have, all the items in A need to be inside of B. So ham is inside of B, cake is inside of B, but cheese is not. So this is not a subset. So it would be false. Oh, I can't change the answer now. Alright, makes sense? Let's move on. Alright, solve power set of B. Anyone want to take a whack at it? So while you guys are taking a whack at it, I'll go ahead and start writing some stuff down. So power set, we know power sets are the only thing with a null in it. So let's go ahead and just throw the null in there, because that's the easy first one to get. Now this one is going to be every combo of B, of like the individual items and the whole thing in total. So it's best to first make or grab every single item by itself. So we can grab B and put B in here. And then we can go ahead and grab D and put D in here. And we can grab E and put E in here. And then G and put G in here. And then the next step, so now we got the individual items out of the way. The next step would be combo. So B plus D. So we would do B and D. And now we would do D and E. So let's do D and E. And then we would do E and G. So let's do E and G. Then we would do, we can't forget the first one and the last one, so let's do B and G. Oops. Thanks for subscribing, Schmizzle. Hopefully that's the right way to say it. We're not going to pronounce anything correct today. Now, we've done all the 2 pairs, so now we got to do the 3 pairs. So there's B, D, and E. So let's grab B, D, and E. And then there's going to be D, E, and G. So let's go ahead and grab D, E, and G. And then we can't forget the first and the last guy, so let's do E, G, and then B. G and B. And then the one final one would be all of them together. So before we submit this, let's double check our work. How do we do it? We just do the normal basic math here. So we have 2 to the power of a number. What's that number? Well, there's 1, 2, 3, 4 items in here. So it's going to be 2 to the power of 4. Don't know how to do that math? Cool. Just let's go to the calculator, right? Let's do 2 to the... I think this one didn't work before. Where's my Wolfram? Here we go. 2 to the power of 4. Oops, gosh. 16. So we should have 16. Oh my gosh. $100 from Blake. Let's go! Scene. Alright. Beautiful. Thanks so much, Slick, for that donation. That is some beautiful, beautiful stuff right there. Alright. What were we doing? Okay. 2 to the 4th is 16. So we should have 16 answers. So let's go through and see if we got 16 answers in here. Oh, by the way, every one of your guys' donations, every dollar that you guys donate is being matched 1-for-1 for the first $10,000. So anyone that donates something like Matthew donated 1, it's actually $2 at the end of the day until we hit the 10K mark. So everything you're doing is times 2. All right, so let's count this up. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we're short 3. All right, we're supposed to have 16. So let's go through here and figure out what ones we're missing. So, I believe we're missing some from the 3 mixture. So let's see, we're missing B, D, and G. So let's go ahead and get B, D, and G. So that's 1 that we were missing. So 2 that we're missing. Do we have B? We have B, E, G. Do we have B, D, G? We do have B, D, G. Do we have... Let's see here. B, D, E, B, G. Alright, I'm not going to spend all our time on this, so we'll go ahead and just take a peek ski, whoops, at the answer here, since no one else put anything else in. There we go. Here's the answer. Here's what we got. Let's see what we were missing. Null, D, E, G, B, D. We're missing B, E. Okay, so we're missing B, E, so one of the normal pairs. We have D, E. We got B, G right here. We're missing E and G. Oh, wait, no, here's E, G. We're missing DG. So you can basically see we're missing a couple of the 2 paired items. And we got 1, 2, 3, 4 3 paired items. 1, 2, 3, 4. We got all of those guys. So it was the couple of 2 pair items that we forgot. Alright. Yeah, mine does too. Isn't there a way more effective way? Yes. Their calculator. Okay. We're doing it by hand right now. This is kind of a stress problem because 4 is honestly the most I would ever want to struggle with by doing it by hand. But in the real world, and possibly there are websites out there that will just give you the answer. So I would just use those, or basically it's just kind of showing off the concept, because when you do write this out in programming, which you'll write something out that does something similar to this, you'll know all the max pairs you get. But like I said, the test is open book, so if you use a calculator to get the answer for it, I mean, There you go. Is a power set, a power set is a set of all possible subsets. True or false? False. That is incorrect. It's true. A power set is a set of all possible subsets. So if we look at our power set, all subsets are listed right here. So subsets are basically all of the items or all the sets that you could make based off of this. If this was like, let's say, your universal set, how many possible sets could exist in the world that are unique? So this would be all of the possible sets that could exist from this set. A proper set is is a type of subset. But subsets are literally anything. Just remember that order doesn't matter when you're using the curly brace stuff. So this is all possible subsets where order does not matter. Trust me, the next part that we get to in the lesson, this will make more sense. We'll have some examples relating this to real world stuff. Is it possible to have an empty set? I know you guys know this one. Well, there we go. True. Yep. So, next, solve. So this is absolute value. So, if we look at A to the power of C, this is an absolute complement, which means it's what? We have to solve this first to get our answer. The absolute value is just going to be how many items are on that list. So if we absolute complement this, which is everything in the universal set here, but taking these guys out, we will get an answer of, yep, 4. Perfect. There we go. All right. So we got, hi there, Bob. Good weather we're having. Question mark. So we need just the absolute value of the new set that we get. This is multiplication. Easy way of doing this. 1, 2, 3. 1, 2, 3, 4, 5, 6. So what's 3 times 6? 18, right? Let me double check myself. I'm scared. 3 times 6. That is not correct. 3 times 6, 18. So let's go ahead and put 18 in here. Awesome. The Cartesian product is not a set of all ordered pairs. And to speed this up a little bit, I'll also show the next one. Is A a subset of B? So we got a true on this one. So we'll review this one in a second. And then do we have an answer for this one? Or was true for this one? Well, this one, I'm going to go with true for this one also because A has ham and it has cake. And they're both inside of B. So it is a subset. So let's look at this guy again. So this is the multiplication So when you're multiplying stuff, is not a set of all ordered pairs. This is not a set of all possible ordered pairs. It's just the isn't a Cartesian product multiplication? Yes, it's the multiplication of two sets, but the what do you call it? The power set will be for all pairs. Where is the? There we go. Oh, we're on this. Is the set of all ordered pairs. So Cartesian product is the set of all ordered pairs. So these are supposed to not be curly braces. So I'll have to fix that in the book because they're supposed to be ordered pairs. But yeah, this is the set of all ordered pairs, and this is not a set of all ordered pairs. So this would be false. I'm trying to think of a way to explain this because you're taking every single item and you're making every possible item with each other item, which the max possible you can have is 3 times 3, which would be 9. So you'll have 9 items in here. We'll move on to the next lesson. I think it will help have some of this stuff make a little more sense. So we're just going to keep continuing on right now. What is a relation? A set of unordered pairs, a set of ordered pairs, a set of ordered pairs, or a set of unordered pairs. I would start there. So we know when we're talking about relations require ordered pairs because that's how you dictate how the arrow points. There has to be order in it. So it can only be B or C. So that can be illustrated by a graph and can't be illustrated by a graph, particularly the directed graph, aka the arrows. So we know relations have to be ordered pairs and you can draw them out with a graph. So it would be B. All right, anyone want to take a whack at this guy? And let's see what the next one is. What is cardinality? A number of elements missing in a set, a number of elements in the set, the number of elements in U, or the number of sets. I think this will be the last one we'll do for this, and then we'll move on to the next lesson. Because you guys are pretty much doing a solid job at this right now. Sure, we got 3 wrong, but I mean, they were just simple little things. Some personal review, it's nothing to be like too worried about. So does anyone want to answer this one? Oh, I didn't realize Twitch chat was popping off also. B for cardinality. There you go. Correct. The number of elements in the set. How about for 11? So let's go ahead and take a look at this. We know this is relative complement. So again, if you forget what it is, you can just go ahead. Relative complement. If I can spell correctly. And it's everything that's not in the first set. So A, nothing in that's allowed from A. So if we go A is not allowed, B is not allowed, so B is here and D is not allowed. So we have E and G. So it'll be E and G. And for this question, we'll have to look here at this guy. Oh God, I did it wrong. It says A. Was that picture deceiving me? A. B, D. B, D. Is it just everything that's an A? Bad pictures. Where's my book at? Okay, it's everything that's an A. Those pictures were deceiving me a little bit. So everything that's an A that's not matching B. So that would be just A, because B and D are also in B. So A is the right answer for that one. Let's see. I gotta go. Great stream though. Awesome. Definitely notes will be shared. Go ahead and ask people on Discord. You guys can share away as you see fit. Let's go ahead and get to the next section because I think it will help with the combination of the math stuff to more of the real world stuff. Let's talk about counting, all right? We all know how to count, right? 1, 2, 3, 4, 20. So, countability helps determine the computability of data, especially when comparing sets. A set is countable if the set has cardinality, all right? So let's go here. Counting arguments. So there are 2 arguments for counting things. Counting arguments follow one of 2 rules for calculating the number of possibilities. There's the sum rule and the product rule. If you remember back to math a little bit, sum is usually together with getting the sum of something, which is addition, and product is usually the end result of multiplication. So all we're dealing with right now is addition and multiplication. Apply the sum rule when counting non-intersecting sets of outputs by adding both sets of outputs together. What's a non-intersecting set? Well, we know that a union is a non-intersecting set. So we can use those types of sets for these outputs. So let's take this example. A principal of a school enters the classroom. Either a teacher or a student needs to acknowledge the principal, say hi or something. There are 2 teachers and 20 students in the classroom. No student is a teacher, and nor is a teacher a student. They are unique individuals. How many possible individuals can address the principal? A lot of words for something that's simple. There's 2 instructors, 20 students, 22 possibilities out there that exist. So this correlates directly with sets, because in a set, every student would be an item and all the instructors would be an item. So this is just you trying to figure out potentially like the statistics of everything. In a sock drawer, there are 6 green socks, 6 white socks, 3 black socks. How many socks must be pulled to ensure at least 3 green socks are pulled? There are 6 green socks, 6 white socks, and 3 black socks. The key word here is must be like pulled to ensure 100%. Sure, you might be lucky and pull 3 socks out and all 3 are the green sock on your first try. We're not talking about first tries, you getting lucky, winning the lottery. We're talking about worst case scenario. Worst case scenario for you to win the lottery is 1 in quadrillion, all right, whatever it is. Just because maybe your buddy went and won the lottery his first try does not mean you are going to get it on your first try. Those odds are always done at the worst possible level, or what's statistically probable. Same thing with this. You would need to pull 12 socks in order to guarantee 3 are green. How do you do that in math? Well, worst case scenario, to get 3 green socks, you would have to first pull all of the white socks out. Then you would have to pull all of the black socks out. And then you'd be able to grab 3 green socks. So 12 socks is the answer. The second example all of the white and black socks need to be pulled in order to guarantee the next 3 socks will be the desired green socks. The product rule, you can apply the product rule when counting intersecting sets. So sets that are intersecting, all right? Not union sets, intersecting sets. Sets of outputs by multiplying all sets of outputs together. So Apple and Android phones allow users to unlock a device with a 6-digit PIN code. How many possible codes are there to choose from when setting up a device PIN code? For each digit, 1 of 10 choices is available, aka you can choose 0 to 9. With this, the range is from this to this, which is also 1 million. So you have 1 million is your possibility. So 1 million is all the possibilities you have. So how do you calculate that in a theoretical sense? I mean, it's really easy because you can see the numbers like 0, 0, 0, 0. Like 6 times is the top number is 99999, and if you include all zeros, that would be 1 million. But to mathematically write it out, it would be every choice you have times the number that you're allowed to choose. So each digit you can choose is 0 to 9, aka there's 10 possibilities, and you can have up to 6 of them. So it would be 10 times 6, or sorry, 10 to the 6th. So you can write it out like this, and you'll get 1 million as your possibilities. So a way that's a little less straightforward, so you can kind of see how this really comes into play and becomes impactful, is another version of the passwords would be if there's a website that requires exactly 2 uppercase letters followed by 4 numbers, then how many possibilities are there for a password? So you have to have 2 uppercase letters. In the English dictionary, there's 26 letters, and they have to be uppercase, so we're not dealing with also the lowercase variants, so just uppercase. So 26 times 26 to cover the 2 uppercase, and then 10 times 10 times 10 times 10 to cover all of the 4 numbers that follow. And you would have this many possibilities of different passwords you're allowed to have. How does this intertwine with sets? Because these are sets. Having 10 of something, it's a set of 10. It's a set of 10 numbers that you can have. It's a set of 26 characters you're allowed to have. They are sets of stuff that when multiplied against each other, you can see what all the possible combinations are. So for example, let's say you're a bad actor, aka you're trying to hack into stuff. You're trying to hack into iPhones, into computers, into servers, and you know that the passwords that are allowed on the machine are only a certain length. You can use sets and relations, what we've been dealing with right now, to now figure out what is the set size for every single character that can go into the password, and do some basic multiplication and figure out all the possibilities there are that you need to potentially be cracking. Then, because you're a programming wizard, you can benchmark your computer to see how fast your computer can crunch through passwords a second. And then from there, you can now figure out how many passwords you can, or how long it would take you to break into the machine. And again, you deal with worst case scenarios. So your time to break into the machine will be if the password was the very last one to be picked. So whatever the worst time is. So that's also another way how all of these kind of diverge together. It's really important when you're building systems, specifically on like optimization, which is one of the last steps you want to do most of the time in programming, how long something might take to do. Because you don't want to be sitting there forever for something to load. Especially if you're building a cool game, a cool app, something like that. Users want things that are quick. How many times have you played with an app or a website where you're messing with things and it was taking too long for something to load? You probably like quit it, moved on to something else, or found an alternative because it was just taking too much time. No user likes things that are slow. We're in a very now age. So you need to be aware, and sometimes you might need to calculate and go with something that may be less secure because it's faster. Let's see, anyone say anything? Nope. All right, let's move on. A password is the most common security device in use today. A brute force attack is a method of cracking a PIN code or password by trying every possibility. Brute force attacks can be made less effective by ensuring complex passwords are used. This is why every website now is annoying you with making sure you use special characters and other crap like that, because it increases the complexity of the password range or possibility range for brute force attacks. Because brute force attacks will always 100% of the time break and crack all of your information. Why? Because it's trying every possible combination in the world. It will eventually crack your password. That is 100% a guarantee. So the security behind it is just choose something that takes a god-awfully long time. If something takes 20,000 years to crack because there's that many possibilities, then hey, if your website leaks passwords, who cares? It takes 20,000 years at current computation times to crack the password. That is why most organizations use passwords with at least 14 characters, with that 14 characters long, including at least one uppercase, one lowercase, one digit, and one special character. You can have up to 20 in the English alphabet, 26 lowercase characters. You can have 26 uppercase characters. You can have 10 digits, and there's 40 special characters, which means every single character that's possible for every one of those 14 characters in the password, there's 102 character possibilities. So 102 times 102 times 102 times 102, 14 times, or you can just say 102 to the power of 14 is this many different possibilities. It's a lot of different possibilities that, you know, that password could be, and it takes a really long time to crack those passwords. And again, this is a set. So if you were to break out this set, kind of like the one time we were doing it and I messed it up and had to look and it was super long, this is what you would have to do effectively programming wise. You would have to make that whole set to make the list of all passwords you need to crack. Let's see. I don't want to use an O of n factorial algorithm on 2 million. Yes, exactly. Can you simplify the sum and product rules? Yes. Sum rule, addition. You're adding everything together. Product rule, you're multiplying. I used the power of right here because I didn't want to type out 102 times 102 times 102, but it's just multiplying everything out. And it's always giving you either the total possibilities available or how many you need statistically to ensure you can do something. So when you're cracking passwords, the password that you want may be the last password that you need to crack. So it would take up to this many tries to crack a password and get into the website you're trying to hack or the whatever you're trying to do. No specific use rules. I don't know what that means exactly. Pretty much sum is addition, product is multiplication. We can look through this right here. The probability that A or B will occur in the sum, aka addition, of probabilities. That A will happen and B will happen, minus the probability that both A and B will happen. And then there is the product rule. When you are asked to take the derivative of a function that is the multiplication of a couple or several smaller functions. Don't worry about that. A lot of math there. It will make more sense when we get into the programming aspect. Basically, addition, and then your possibilities, and multiplication, and then your possibilities. Any questions on this? Let me check the Twitch chat here. All right. Pigeonhole principle. The pigeonhole principle states that if n items, so n is just any number of items, you give a number and we'll put it there. So if any other of items are put into some number of containers with the number of items are greater than the containers, then at least one container must contain more than one item. To simplify it, if I have 5 apples and I have 4 containers, I have more apples than I do containers, aka n is greater than m. I have more items than I do containers. Then that must mean that at least one of the containers must contain more than one item. So after I put all these apples into the containers, one of them will contain more than one item. Let's see here. In a group of 20 students, there must be at least 2 who were born in the same month. Because there are 12 months in a year, and so if we look at the formula now, there's 20 students, which is our items, and there's 12 months in a year. So we got 12. There are more items than there are containers. So that means for a fact, 100% of the time, there will be at least 2 students that were born in the same month. Imagine that students are as pigeons and the months as pigeonholes, figure 13. No matter what pigeonhole each pigeon lands in, there will be at least one pigeonhole with at least 2 pigeons. To calculate how many pigeons must share a pigeonhole, divide the number of pigeons by the number of pigeonholes. Round up by 1 if there's remainders. So another version of the problem reads, in the sock drawer, there are 6 green socks, 6 white socks, and 3 black socks. The ones that we already, the question we asked last time. How many socks must be pulled to ensure at least 3 of the same type? The answer is 7 socks. So 3 of any given type. So this is again based off of worst like case scenario, aka you go container by container. All right, you draw 1 green sock, you grab 1 white sock, you grab 1 black sock, you grab 1 green sock, you want 1 white sock, 1 black sock, 1 green sock. There you go. That's how many times at maximum it would take you to ensure you would have 3 socks of the same type. With standard distribution, 2 of each sock would be pulled, guaranteeing the next sock would be a 3rd match sock. This is a lot of this is dealing with worst case scenario stuff. So yeah, sure, there may be 20 students that were born on the same month, but that also answers the question because you have to guarantee at least 2 of them were born in the same month. So it's just guaranteeing the minimum, basically. Like the minimum amount of work you have to do something. Like correctly. Does that make sense? So again, the counting arguments, sum and product, addition and multiplication. Adding stuff up to figure out worst case scenario, or multiplying stuff together to figure out worst case scenario. Pigeonhole is figuring out what you would need to do to ensure the least amount of work for you to guarantee something. If that was at all confusing, don't worry. I got some videos for us to watch. Are there any questions before I play these videos? And also, now you guys probably hate birds, and it's okay. Any questions? Alright, I'm going to pause the music now, and we're going to take a look at one of these videos, or both of the videos. Let me pull this up.
Today we'll talk about the pigeonhole principle. This is huge. This is a very, very important thing. Like I said before, a lot of proofs are done by contradiction as a proof technique. This is a very nice method of proof that is used to solve some very, very important things. So let's talk about it. What is the pigeonhole principle? On the left here, I have a bunch of pigeons. We can also call them items. And on the right, we have pigeonholes, which we can also call containers. Pigeonholes are just places where pigeons go. And the question is, when we distribute these pigeons into the pigeonholes, what do we see? What is something that we always see? Okay, let's do this. Let's put this one in here. Let's put this one in here. Let's put this one in the first one and this one down here. So then we have a 3, 0, 1 distribution. That's nice. So now I say, well, okay, actually I want to distribute all these pigeons, but only have 1 in each box. So we say, oh, okay, let's put this one in here, this one in here, this one in here. Oh, crap, what do I do with this extra one? Well, let's break the rules and just put it in this one box up here. So we have a 2-1-1 distribution here, and the pigeonhole principle states that if you have more pigeons than pigeonholes, there's always going to be one pigeonhole with more than one pigeon in it.
So that's another breakdown of it. Another real world example, let's talk about games, video games. Alright? You want to make the new Call of Duty because that's an original idea that's never been executed on before. Alright? Let's call it Battlefield. Alright? Battlefield 8. Alright? You need to host servers to have the players play on them. How many, if I tell you your game has 10,000 active servers, how many, 10,000 active players, how many servers do you need to have and to ensure that everyone has like a max full lobby? This is where this would come into play. This is where it will help you figure out exactly how many boxes you would need to generate in order to make sure everyone has a pretty full lobby. Because if I join your game and there's 10,000 people online and I'm in a server of 2 people, like, I'm gonna be like, this is some whack crap. Like, I'm done with this game. I'm gonna move back to Call of Duty. Alright? If you guys want to watch this video in more in depth, it will be linked in your guys' companion guide that we'll send out later today. Any questions on that before we move on? And this one, I believe, is a pretty long
Today
video.
we're going to learn how to count, and we're going to start with some very simple tasks.
Yeah, let's watch the beginning of this one also, and then you guys can watch the rest in your companion packet.
Get more complicated when we start to do more than one task in a row, or we have two separate tasks that we're doing simultaneously. But first, a very easy question. How many ways can you roll an even number on a 6-sided die? So let's just specify this, that this is for sure 6-sided. Well, which even numbers do you see on a 6-sided die? You see the numbers 2, 4, and 6. Okay, so there's 3 different ways that we can roll an even number on a 6-sided die. Okay, easy question. How many ways can you draw a face card in a standard 52 card deck? Well, what is a face card? A face card is any of the Jack, Queen, or King, and of course for each of these Jack, Queen, and King we have 4 different suits. We have hearts, we have diamonds, we have clubs, and we have spades, all of which I am not good at drawing. So in total, we have 12 different ways that we can draw a face card from a standard 52 card deck. There's 4 jacks, 4 queens, and 4 kings. Okay, so this is just doing one task inside of some specific domain. We have this thing called the addition rule, and this is when we have 2 different tasks, A and B. So we could say that A is rolling an even number and B is picking a face card.
So that's what he literally just did right here, is the addition rule. He used basic addition, adding up things to figure out there's 3 possibilities for this one,
Is that we can
and there's 12 possibilities for this one. So try not to read into it too much. It's pretty much like basic, what you've probably been doing naturally. Again, it's just a word that's associated with the thing that you've probably already been doing. So he'll also go into the product rule, which is multiplication. So doing the same thing except multiplying for certain things. So we'll add this into your guys' packet also. Is there any questions on that? Are you guys ready for a break? We're almost... Oh, whoops. My bad. There we go. So I said we'll include those in the packets. We're about to go on another break. Let's take a look here at what we've gone through. Sets and relations. Congratulations. We're completely done with all of this. We're completely done with sum rule. We're completely done with product rule. We've covered the pigeonhole principles. You guys, there's only 8 items on this list, and we are now halfway through. You're almost done with all the math stuff. So, hallelujah. This is, like, thank God. This stuff is pretty much almost completely, like, done with. All right? This is all the non-fun stuff that at the beginning we have to front load, because trust me, it's good to know some of these concepts going into programming, because it will make you 20 times better than everyone else. You don't need to know it like a pro. I don't really know all of these like a pro, all right? I'm not a math magician, all right? But knowing them can help you figure out problems when you're programming. Programming isn't really like math intensive like how this stuff is, but you'll see the correlation here in a little bit when we do get to that part. Any questions right now before we go on to break? And we're going to do just a little bit of basic logic, and then we're going to call today good. And then we'll continue tomorrow. So I guess before we go on break, I have to fly out to California tomorrow, so I won't be able to do the 1 p.m. Eastern Standard Time. So we need to do a later time tomorrow. What works good for everyone? Let's say anytime. We can do any time between like 3 or 4 p.m. Eastern Standard Time to like 9 p.m. Eastern Standard Time. For those of you on the Pacific Coast, that we're 3 hours ahead. So you guys go ahead and put in the chat what you think would be best for you guys, and we're gonna go with that for the next 3 days, because I'll be in California tomorrow, the day after, and then one more day after that. All right, so let's go on break. We'll be back in like 3-ish minutes. All right, we're back, and I gotta put up the green screen. There we go. So we're back. Let's see. 4 to 6, 6 p.m. Let's do 6 p.m. Eastern Standard Time. We can make that the official new time also if that works better for y'all. 1 p.m. was chosen kind of generically, all right? We didn't read into stats or anything too deeply. We just kind of plucked it out of thin air. So we'll switch it for the next couple of days, and if that works better for everyone in general, we can keep the later time. So, where's my mouse? Oh, there it is. All right. Were there any other questions? All right. So, is my mic like peaking or too loud, or is it just fine? I don't know if I messed up anything here. But we're going to be getting into Logic Book. This is the most of the important things that we're going over. Everything else is good to know, kind of good to have in the back of your head. But logic is what runs all of programming. This is really the thing that will tickle and mess with your mind at first. But it's the barrier. Even if you don't learn this part that we're going to be going over, if I were to teach you programming right now from scratch, if you were going to a coding boot camp right now from scratch, you will still run into this issue. It won't be laid out or worded the same, but the logic of how you program and do things, like how you put all the puzzle pieces together effectively, still takes a second, and a little bit, practice for it to finally like snap and make sense to you. This is the mindset. What's the best way to get into this mindset? I highly recommend, if you aren't already, go to YouTube, type in TED Ed logic puzzles. All right, they have so many of these. Watch them. A lot of them at first may like stump you, and you don't need to, it's not really the super mathy heavy ones, because some of them are like more heavy on the mathy side. It's just the concept of the logic. For example, here's a simple one. I got 2 pieces of rope. All right, 2 pieces of rope. Let me see. Do I got string or something I can hold? I got a phone cable here. Right, hold on. Let me find some phone cable, and we're gonna use that instead. Here we go. Oh, come on. Oh God, why is this cable so long? All right. 2 pieces of rope. All right. I'm gonna move off this to clear everything out. 2 pieces of rope. All right, their length exactly the same. They're both exactly the same in length. You're stuck in the cave in the middle of nowhere, and you need some light to navigate the cave a little bit to find a safe place you can hunker down. All right, all you have is 2 pieces of rope that you can burn to give you light. Well, actually, hold on. Let me rephrase this. You need to make a crossing over a river. And to make a crossing in this river, you talk to this old dude. And this old dude was helpful, but not helpful. He handed you these 2 pieces of rope and said, both of those ropes will burn for 30 minutes. If you light them, they'll burn. It will take from one point to the other. It will take 30 minutes for a piece of rope, and you have 2 of them to burn, aka 1 hour of timing. There's a river that you need to cross, and in exactly 45 minutes, that river's current will be slow enough where you can cross it without being swept downstream and killed. All right? So you need to cross it exactly at 45 minutes. If you cross too early, you're dead. If you cross too late, you're dead. The catch is the rope does not burn evenly. So if the rope will always burn for 30 minutes, but if I were to light one end of this rope, it might burn through all of it except for the very tip right here, and this will last for the whole 30 minutes. Or it might be more even where the whole thing lasts 30 minutes. You don't know. How do you tell 45 minutes with those two ropes? Give you guys a second to think about it. If you need clarification, go in and ask questions. This is logic. These are the logic puzzles. This is the type of thinking that you have to have in order to like really excel at programming. And it's just a mindset. The more you do these, the more you'll just be in that mindset naturally. It's kind of like a friend group. The more you're around like certain friends, the more you'll kind of like be like them, enjoy their stuff, like do stuff that they do. It's the same thing with these puzzles. The more you're around them and you do them, the more it will just naturally make sense for you guys. So any guesses on how you would tell 45 minutes? See, I could never get them right, but they're fun to try. And then learn how it would be solved. Yep. Any guesses? I'll wait another minute for you guys to guess, and then I will give the answer. Wait, what was the question again? All right. To summarize the question, you need to tell when 45 minutes have passed. All you have at your disposal is two ropes and technically a lighter because you need to light the rope. Each rope will burn for 30 minutes, but each rope burns unevenly. So the whole rope might burn in 1 minute except for the very last part right here, and it might take, this last part 29 more minutes to burn. It's unevenly burning. So how would you figure out how to tell exactly 45 minutes? What if you cut the rope before you burn it in half? Is that 15 minutes? So we burn this whole rope, and that takes 15 minutes. Then you're saying the second one we would cut in half, and you're saying that would take 15 minutes. Well, since the rope is uneven on how it burns, you cut it in half, and the half that you just cut, you light it, and it burnt up in 30 seconds. And then you go in the river, try to cross it at the wrong time, and then you die. So that would not be the answer. That is the typical answer people do right off the bat, though. So that is a good guess. I'll go ahead and give the answer. So this is what I mean by, but we know it burns for 30. The whole thing will burn for 30 minutes. Guaranteed. You just don't know. It unevenly burns through every part of the rope. So you don't know, whether this section might take 10 minutes and this section might take, 1 minute. It's uneven. So the solution is simple, but the point is it's the thinking, the mindset behind it. You can't simply cut it in half because it's uneven, so you can't trust it. But what you can do instead is burn the first rope, because that will take 30 minutes guaranteed. And the second rope, you just light both sides of it. Because it's going to take 30 minutes to burn through the whole thing. So if you light both sides, it's burning twice as fast. So it will be exactly 15 minutes for it to burn completely. Now everyone says, oh, that's dumb. Yeah, it is. But that's what I mean. It's just that mindset of thinking about things differently. That's what logic is, and logic questions, and how you can gauge like how well you'll be able to think about like programming stuff, because it's not hard. Like that question isn't really hard per se. It's just differently like thinking about a solution. Does that kind of make sense? Does that answer make sense? Do I need to review any of that? Oh, I just saw your response, Kauai, in the Twitch chat. Sorry, I'm having to like go between them. Yeah, so when we're going through this logic stuff, don't get too hung up if you don't understand things right away. That's fine. It takes practice. I highly recommend binge watching these TED Ed videos. Mostly they're entertaining, but second, it will really get you into that mindset, and it will literally help you be a better programmer, because you'll be able to think about the programming things you have to do, like making a game or making a server or whatever you want to program out. It will help you think differently and more like a computer, because computers are binary systems. It's either a 0 or a 1. It's a true or a false. You can only do one thing or the other. So it's a very like what's the word for it? Basic. I was trying to think of a fancier word for basic, but it's a basic way of thinking about things in general. Normally as humans, we are not basic thinkers for basic logic. We're thinking about a lot of things and how everything affects each other, and everything's on a spectrum at the end of the day, and everything's gray. It's not black or it's not white. If anyone tries to sell you on black or white, they're a scam artist, all right? Everything in the real world is a scale. It's all gray area. All right? So let's get into this a little bit more. So basic logic is a tool used to create and understand a proof in either a formal symbolic proof or a less formal but still mathematically rigorous argument. It is essential in formal specification, verification, databases, and cryptography. So if you are having people log into your system, how do you guarantee the login system is safe? You can be like paranoid and try to do things and twist knobs in different ways to maybe make sure it's safe, or you can sit back, relax, eat some food, whatever state you're in, maybe smoke a joint and like think about it deeply in more of a basic logic standpoint, and you'll find that you'll be able to create something better and more robust that way. Same thing with databases, which if you don't know what those are, don't worry, we'll get into it. And cryptography, which is basically encryption. All right. So, translation of propositional logic. Many proofs in mathematics and many algorithms in computer science use expressions like this. If you've done programming, you've probably seen this before. And when we did our stuff here, you saw I used something called an if statement. And when you read it out loud, let me get rid of this second section. It literally reads almost like a sentence. Like I wrote this out in a book and I gave it to you and you read it. Like, if the user's input is in my set A, I can usually take that, like how I just said it, and tell anyone in the world, and they'll usually understand kind of what I just said there. If the user's input is in the set A, or is in my set, all right, they'll be able to typically figure that out. That's the propositional logic. So if something then something. So the then in this programming would be print, it's a set. All right, it's the action you take. So if something is true, then perform an action. If today is sunny outside, I'll go outside and enjoy the sun. If it is rainy, I'm going to stay inside. In reality, if it's sunny or if it's rainy, I'm probably going to stay inside. But, and you can see here, you can use things like and or. You know, if it's sunny and it's above 80 degrees outside, then I'm going to the beach. And then I'd give the example of if it's sunny or it's rainy, then I'm probably just going to stay inside, all right? It's just that type of basic logic of, oh, if something and then something else. It is necessary to know the cases in which these expressions are either true or false. A proposition, so another fancy term, definition that you guys need to know, or a statement. So I gave a bunch of statements. The fancy way of calling statements is a proposition. Is a declarative statement that is true or false, but not both. Because again, we're dealing with computers, which are binary systems. It is one or the other. It is a 0 or a 1. It is true or false. You cannot have both. It is one or the other. It is black and white. This is not real world. This is computer, math, logic world. Consider the following examples. Ice floats in water. That's true. China is in Europe. That is false. 2 plus 2 equals 4. That is true. 2 plus 2 equals 5. That is false. These are all accurate propositions. Where are you going? That is not a proposition. That is a question. Do your homework? That is not a proposition. That's a statement. All right, the first 4 are propositions, while the last 2 are not. Also, 1 and 3 are true, and 2 and 4 are false. So that's the difference between propositions and like other verbiage you might give. It has to be a straight up true or false statement that you can like evaluate. But again, this is where the divergence from computer world and real world start happening, because ice floats in water. In real world, that's a gray area. Ice doesn't always float in water. It depends on a lot of things. Salinity, non-salinity, I don't know, just science stuff, all right? The ice could go underneath the water. Same thing with China is in Europe. Well, like, if China owns companies that are in Europe, like, China is in Europe technically, but that's the gray area. Real world is always gray. Computer world is just one or the other, all right? This is where things diverge. So don't go to your girlfriend or boyfriend or husband or wife or whatever and try telling them that you now know logic and you're always right about XYZ, because you're not. You are right in computer world. This ain't computer world, all right? Any questions on this so far? So you can go and ask your questions. I'm going to keep going on. So when a proposition is made of sub-propositions or connectives, it's called a compound proposition. In English, it would be called a compound sentence. Fundamentally, a compound proposition's truth value is determined by the truth value of the sub-propositions and how they connect to form a compound proposition. How do you make a compound statement? Just like in English, it's just an and or an or. That's all you have to do to make a compound. So a proposition, in the sense it is the smallest little bit of English that you can say that is definitively true or false. A compound proposition is when you have 2 or more of these smaller propositions that then you can evaluate against each other to figure out an overall true or false for it. Message was redacted. What did you say? No, I'm curious. So let's look at these examples. For example, proposition 1 through 4 above, this should be, is it above? No, below, I don't know why it says above, are primitive propositions. Oh, these ones. These ones are primitive propositions because they're just single small items. By comparison, the following 4 propositions are a composite, aka they're compound. They're multiple things together. So roses are red. That is your proposition. That is your smallest piece of logic. You are claiming, true or false, roses are red. And is your compound, violets are blue. If both of those are true, then this statement is true in general. So truth value is just how true a proposition is. Yes, it is either, the truth value is either true or false. There is nothing else. There's only those two. So John is smart, or he studies every night. So this is true because you're claiming John is something. He is true. So that is true. He is smart, so he's true. Or he studies every night. So you're claiming that he studies every single night. So that is true that he studies every single night. If Sue has a dog, then she likes animals. All right, you're making an assumption basically. If an accumulator is positive, then memory location 4 to 5 is set. All right, this is some assembly stuff. If any of you guys get that. So the logical operators you can have is an or, a not, an or but not both, an if then, and an if and only if. And these are all things that are in every single programming language to some extent. All right. So these also have their own terms: conjunction, disjunction, negation, symmetric difference, conditional, and biconditional. All right. All of those relate pretty much one for one with programming. So let's look at some programming comparisons for Python and how you would do the equivalent in here. And again, the programming stuff, you learning Python from scratch, if you don't know Python, we'll do that at a later time. This is just me showing you that there is, for a fact, a guaranteed connection between all this madness. So let me make this zoom in a little bit more. Let me know if you guys can't see this. So pull this off to the side here. Conjunction is an and statement. So if we say, if, well, we can do this. Let's say 2, let's say 3 and 3. All right. And state, or what's this called? A conjunction equals. So this, is this even valid Python? It might be 3 and 3. It is, didn't expect it to evaluate to that, but an and statement is something you can do in Python. You can say and do multiple comparisons. So I can say, I don't know, roses are red, which is true, and violets are blue, which is also true. So that is a way you could do a conjunction in programming, is using the term and. Both of these must be true, and if both of these are true, then the whole statement is evaluated to true. If I put it in here, you'll see its output is true. If I do this again and change one to false, well, now if either one of them are not true, then the whole thing is false. So next we have or, which is a disjunction. Equals true or false. So or will always be true if at least one thing is true, because it's either this item or the other item. All right, whatever one is true is the true item. There's not, which is negation. So negation, I can literally say not true. Literally like English, if something's not true, it is false. Correct. You guys are right. Now there's symmetric differences, which is or but not both. These are going to be a lot more to type out. There's conditionals, which you guys have seen right here. This basically evaluates to if true, then this next line is the then do this action. And by conditional is if and only if, and that's what this also does to an extent. We'll get through some more examples here in a second, and there's some cheat guides basically that will show you guys so you can easily evaluate these. Are there any questions on this so far? So there are more special symbols for us to learn. Yay! The word and can be combined with two propositions to form a compound proposition, which we already went over. It's just using the word and. The symbol, because there has to be a math symbol for it. I mean, using and was just too easy, right? We had to throw some math stuff into it. Is this. It literally looks like an A, but it's missing the center part. That's how you know it's an and. So when they say something like this is you evaluating something and something else. It is read as P and Q. Since P and Q is a proposition, it has a truth value. And this truth value depends on the truth values of both P and Q. Specifically, if P and Q are true, then P and Q is true. Otherwise, P and Q is false. The truth value of P and Q may be defined equivalently on table 1. So this table right here defines this whole thing for you. This is every potential possibility you have. So let's go into programming world and let's look at our programming example here. Give me a letter. So the user is going to give a letter. If the user has given me a letter and the letter is user input is A, then that is true. Or what we can say is, if they've given me a letter I'll just do this. If they have given me a letter, just something in general, and it is A, then it is true. So that is the and statement. So roses are, well, that wouldn't be, there's no and in it, but there needs to be an and. So basically, the propositions in Englishtown are going to be stuff like roses are red. That is your P. And then there's the and word right here. And Q would be violets are blue. So if roses are red, which is true, so there's a T right here, and violets are blue, which is a T right here because it's true, then you know that it will always be true. And if you have any of these other combinations, your result will be false. Any questions on that? The first row, you can ask your questions as we move through. Can you see? Can you move your head? Oh, this is the answers I was getting. My bad on that one. I'll try to pay attention to that next time I'm doing stuff on there. So the first row says that if P is true and Q is true, then P and Q is true. And the second row says that if P is true and Q is false, then P and Q is false. So basically just going through this table right here. We don't need to go through this little last part here, but this is basically your shortcut guide here. Let's see. All right, this book is a little long, so I think we'll end it right here. Just a little taste of logic. It's if and then statements. It's just straight up, if I state something like roses are red, is that true or false? And then you evaluating it. And when you evaluate multiple things together, those are called compounds, compound propositions. And you can use stuff like and, or, not, or but not both, if then, if and only if. So just different ways of you using normal English verbiage. So we'll continue tomorrow on the logic train. And I promise you, this stuff isn't too difficult, mostly because we just draw out tables, and the tables will tell you the results. And then there are truth calculators out there. So we'll go over utilizing some of those truth calculators to help you speed up some of these evaluations and processes. That sound good? Any questions on anything at all, what we've gone over? What time will tomorrow's stream start? I think we came up on 6 p.m. Eastern Standard Time. Will be the stream for at least the next 3 days. And if people like that time, then we'll stick with that time moving forward. If not, we'll revert back to 1 p.m. But it's totally up to the general population here on what time you guys would prefer, and we can move that around. So I'll stick around for another second. You guys can ask questions. Again, if you are subbed to our Patreon or to Discord Premium, and you at least on Patreon, you have to be at a Patreon tier that allows you access to the Discord channels. In support chat, we will be dropping companion guides, which are going to be the overviews of everything we covered, with some links to YouTube channels and some extra questions, and then flashcards that anyone wants to make. If you have anything that you want included in this, you just let me know, and we'll throw it up there if it's at a decent enough standard where people will understand it when they look at it. All right, sweet. If there's no other questions or anything like that, I guess I will see you guys tomorrow. We'll have the guide out hopefully in an hour or so out to the supporters chat, so you guys can get access to that. If you have any other questions, comments, concerns, you can ask them in the Discord at any time and we'll address them. If you think something was blown through too quickly, or you want to review something, just let me know in the chat and we can change things up for the next stream. If you think something will be conveyed better in a certain way, let us know and we can definitely adjust accordingly on stream. Everything is totally up to you guys that are participating. you guys can guide this however you need it to be guided for you to learn maximally. Alright. We will see you guys all on the next one. Adios.